All right, everybody, welcome back to day 2 of Optimization 101 for data scientists. I'm excited for everyone to be back. I hope you enjoyed the first day of content and was able to go back and maybe review some things that may have been a little confusing and be able to hop into some of the exercises and get all that stuff taken care of and done. I also, as a little quick reminder for the first modeling example, had a couple bonus questions at the end. I don't think we'll have time to review them today, but definitely take a look at those when you have some free time. So before we get into the second example today, I'd like to just take a minute to go over what the agenda is again, just to make sure that it's clear, and then we'll hop into the second example. So starting now for the next hour, we're going to talk about the second modeling example, which is about renewable energy and energy storage. And then after that, we're going to have a half hour to introduce some exercises and then go over those exercises that have to do with the problem that we go over, and then also some sort of logic modeling type of fun stuff, I think. Then after that, we're going to dive right into a quick 15-minute presentation from Hassan about the final problem. Then it's a little bit of a break at 12:45 Eastern. We have a 15-minute break, grab some water, stretch out a little bit. And then we're going to dive back into modeling the example that Hassan has just described in the previous session, and get hands-on there for the next about two hours we have available. We'll see how much of that time we need. But and then after that, there's going to be a quick 15 minutes pre-recorded video to wrap everything up, and it'll help you understand sort of some next steps for optimization modeling with Gurobi. So without further ado, let's share the screen. All right. So our second example, our second modeling example is all about utilizing renewables and energy storage. There's a lot of text here. So if you come back to this, you can get a sense of what's happening and everything. But I'm going to just go to this picture real fast and use this. So essentially, we have a university building that's holding classes for a week. That building is connected to the grid to get electricity, but also a couple batteries, which are connected to a solar panel. So the sun shines, it shines everywhere, but the solar panel can pick up the energy there and store it into batteries, and then that can feed meet the energy demands for the building. And the energy demands for the building depend on sort of, there's like a fixed demand for the building itself, but then the number of classes and what hours they're busy and stuff like that also influence the amount of electricity that's being used. So all of that data you can look at separately and get a little bit of a better sense of what's going on. But we're gonna hop right in now. So this is essentially that was a quick review of the problem. It's not super complicated, but I think a quick visual was a better way than going through all of this text. So this is a quick visual of what the schedule looks like. We sort of just made up courses, made up timeframes, and also made up the demand for each of these individual courses. But this just sort of gives you a general sense of how busy things are, more or less, for a particular week. The problem is to take a week's worth of classes, and then let's figure out the best way that we can utilize the solar panel, utilize the battery, utilize the grid in order to meet demand, but then also meet demand with buying as minimal amount of energy from the grid as possible. So we want to minimize that purchase, just the raw amount, not the cost, at least for the first go around. If we have time, then we'll change the objective to include a price and see how that changes things, seeing if we have enough time. So the solution approach that we're taking to this, similar to the previous problem and a lot of problems that we've been talking about, we have a forecasting component, a machine learning component, and then an optimization component, where the machine learning part builds up some sort of forecast, builds a predictive value, and then that is fed into an optimization model as a parameter. We did solar power forecasting on actual data, and that is in a separate notebook, completely, off to the side. We used profit for time series forecasting. There's a bunch of ways to go about it, a bunch of to build a forecast using the data. It was just one thing that we were like, hey, it'd be cool to use this. So feel free to dive into that, mess around with that, do a whole bunch of different ways of producing that forecast some other time other than right now, because we're going to focus on the optimization part. But the notebook is there for you to look into at your leisure. So the goal of this problem is to essentially build the optimal battery schedule, because a battery, a rechargeable battery, something that can charge, take in electricity, and you also discharge to meet demand. So essentially what we're trying to find is, hey, are there times in which there's sort of excess solar availability that we can use to charge batteries, and then when the sun's maybe gone, we still have higher demand, or the sun's not as prevalent, and we have higher demand, then we can use the energy that's stored in the battery to meet demand there. And then if all of that doesn't work, we still have excess demand that can't be met, then we can buy energy from the grid, but that's what we want to do minimally. So let's look into our sets and indices. We have two batteries, battery 0, battery 1, and then we have just time periods. We have 180 time periods that represent the week. We did a little bit to make this problem fit into the sort of the pip install version of Gurobi Pi, that license that comes with it. We sort of lopped off a little bit of the time. So I think the times begin at 5 a.m. and end at 8 p.m. So just a little bit of trimming the problem to make sure that it fits nicely. So that's why we don't have as many periods as you might think. And the periods are 30-minute intervals. So we have our sets, we have our indices. Let's start inputting that data. And then also we have the solar values that are predicted from the previous, from the machine learning model. We're going to be reading that in as a CSV. So that file is called predicted solar values.csv. And by setting the batteries here like this, that's creating that set. And we're just taking the range of the number of periods to get our set T. So I've already ran that. So now the input parameters, there's a couple things that are important about using batteries for something like this. Is we can't have a battery has a capacity, it can only hold so much energy. So that's an important value to have. So we have a capacity for each battery, which is C sub B, and then in the code it's just capacity. There's also, when you transmit energy, there's also a loss. And we're going to account for that loss. And we're going to make a little bit of a simplifying assumption and put all of that energy loss on when the battery is charged. So once there's energy coming into the battery, there's going to be a loss there. When it comes out, we're going to ignore the loss. It's a little bit of a simplifying thing. You can, expand to not worry about that. But we're going to do things a little bit more simple here. There's also an initial energy, what's already in the battery. And then we have our solar power generation of the panel for each time period T. So that's each of these components down here. We're assuming that the batteries are empty to start with at the beginning. Here's our loss. It's essentially, I say it's P loss, but it's essentially what is not lost. So we have a 5% loss here and a 10% loss here. And then the capacities are 60 and 80. So now we need our demand. And this is something else that there may be data behind this to build this demand. We're going to sort of just say it's a fixed number. And reading in each of these CSVs as well, we have a schedule. We have demand that's based on the schedule itself. So the classes, what each individual class brings in terms of energy demand, and then also the average building, like a building demand as well. So this is sort of the two sources of electricity demand that we have, and we're just going to add them together and say, hey, it's one value, and keep that simple as well. So let's add up those values just to see sort of where we stand, and we see that our demand is 5,250, and our solar generation is 4,939. So that tells us at least one thing off the bat, is that we're definitely going to have to buy some from the grid. So it's good to understand that that's going to be the case. Now let's just see, how much we can how well we can use the batteries to minimize what we do buy. So we know at least how much we're going to have to buy, but maybe it's a little bit more. Our decision variables. So we have a lot of decision variables, or at least a lot more than what we had before. So as I mentioned sort of at the beginning of this whole training, is that we're going to start pretty simple, and then we're going to get a little bit more complicated, and maybe quite a bit more complicated depending on how experienced you are with optimization modeling. And I think this is going to be a decent jump from where we were yesterday. So I'm going to try and go slowly and make sure that we understand everything that's happening, because the constraints and stuff like that are going to be a little bit more complicated than what we had yesterday. But it is going to be a nice build up to the problem that Hassan's going to be talking about later. So there's some similarities there. So it'll help down the road as well. So we have a decision variable for each battery and for each time period about how much we want to charge. We're going to call that F in, and then how much we discharge, which we're going to call F out, or flow in and flow out. And then we're going to set a max amount of how much each battery can charge or discharge in a single period to be 20 kilowatts. So those are our first decision variables, and we have this ran already. So we know how to do this. This was from yesterday. Add vars. We put the sets that we want for indices, and then we name the constraint. So then next, other things that we can decide. So we're deciding how much to charge and how much to discharge. And the next thing we can decide is, well, how much energy do we want to buy from the grid? So we need to come up with a decision variable for that. And that is just going to be indexed by time. And one assumption that we're going to make for this is that the grid decision variable, is going to be non-negative. So we can't sell back electricity to the grid, although that is an interesting problem, and sort of energy arbitrage, and see how you can strategically use solar and other renewable resources and storage to sort of take advantage of that. But we're going to not worry about that for now, make things a little bit more simple. So that's another option. The next two sets of decision variables are going to have a slightly different feel. It's not something, they're not going to be things that we directly decide, but they're going to be results. They're going to be things that are resultant from the previous decision. So depending on how much grid we have, how much we charge and discharge, we're going to have to keep track of other amounts. So it's often beneficial to create decision variables for these things, because it makes things more readable, makes it easier to code, and stuff like that. And it also helps with modeling the constraints about how things need to work from one time period to the next. Just makes it a lot more simple. So we're going to keep track of the state of each battery. So essentially how much energy is in that battery for each time period. So that is going to be S sub BT. And then also the amount of solar energy that's used in a period. We don't have to use everything, and sometimes we can't use everything. If our batteries are all full and we have zero demand, doesn't matter how much the sun is shining, we can't use any of that energy. So it's also something that we're going to consider a decision variable, because it's based off of all the other decisions that we have. So far so good. Any questions? Is there anything? I'll give a minute or a little bit just to sort of rehash this. I think it's worth sort of going in again. We have a flow in and flow out decision variable. So how much are we charging and discharging for each battery, each time period? How much we're buying from the grid, just the raw amount of electricity for each time period, the state of the battery, which is going to depend on all of those other things that we do, and how much energy we're going to be using that's from the solar forecast. Okay. So there's one last decision variable that we need, and it often comes up with problems that arise like this. Right now, there's nothing that we have saying, I'm going to go back up a little bit, that our flow in and flow out can't be both positive at the same time for a particular battery at a given time. So right now, we don't have anything that's saying you can't charge and discharge at the same time, but we know that that is not possible. So we need a binary decision variable that limits what the batteries can do each time period. So, and particularly, we need to make sure that at each time period, the battery is doing one of three things. It's either charging, it's either discharging, or it's doing neither. It's just sitting still. Those are the three options. So to model this, we're going to introduce a binary variable, and commonly use for some of these, a lot of people like to use just a lowercase z as the binary variable. It's going to be indexed by battery and time. I like to call these things switches. I just started using that when I was way back when, and it just sort of stuck with me, and it's just a fun word to say. So let's actually take a quick reminder from what we learned yesterday. Sometime learned it a little bit of a hard way, I guess. Is all right. Now we have a binary decision variable. We didn't. There's some question marks there, so let's fill in the question marks. So we have the index. Batteries. So we have our first index, or for our first set, we have our second index, so B and T. Now we need to make sure that we explicitly say that we have a binary variable. So that's V type equals GRB binary. All right. Cool. So so here's where I'm gonna do a little bit of, give you guys a minute to sort of think about some things and see if you can fill in a couple blanks here. So, but first, I'm gonna go through the first constraint. So there's a lot of math on this, but let's sort of think through it this bit by bit. In each period, we need to make sure that we meet energy demand, which I think actually I forgot to talk about. Maybe I skipped over it. That is D sub T. Is the amount of demand, energy demand at each time period. But there are three sources that we can draw from. We can get stuff from the grid, we can get stuff from the solar panel directly, or the battery discharge. So those are three ways that we can help meet demand. But we also have the option to charge the battery, so we can take from that. So this is our grid amount right here. This is the solar generation amount right here, indexed by T and T. And then here is for each battery, we want to sum over the amount that is discharged that helps meet demand, but then also take away what's coming in for charging. So this is essentially, all of our sources of energy. And you may be a little bit more comfortable with like putting this on the other side and thinking about this is all of our things that produce, the F out, generation and grid, and then all of our things that sort of draw in the electricity is our our battery charging and our demand. So that may be another way to sort of put everything on one side that that's one part of this constraint. And then everything on the other side is another part, that's definitely doable as well, if you'd like to sort of separate it out like that. So there's a lot here, but what I want to give is like a minute to see if you can at least think through how to write the quick sum constraint. So I left some question marks here. And it essentially, the question marks go from here to here. We have the 4 T and time periods, which is here, so you don't need to worry about that part. But I'm going to give you just like a minute to think about that, maybe start typing it up a little bit, see if you can figure out what the constraint will be. And another note is we're making sure that we meet demand exactly. You could have a greater than here, but that's just, typically in these models, we want to make sure that you meet demand exactly. There's no real reason to have more energy available than you have for demand. So unless there's other weird constraints happening that we wouldn't have, this would be at equality anyways. And as a quick review from yesterday, when inequality constraints are at equality, they're called binding. So I'm going to give about a minute to go through this and see if you can come up with that constraint. Let's go through this a little bit by bit. So we need to quick sum over what goes out and what goes in, accounting for this loss. So we are quick summing over flow out minus our loss, which again is just the proportion that still survives. It's accounting for loss. And then since we're summing over B, and we're summing over all of this, I put the extra parentheses in there just to make, you could distribute and reform, you can, do a whole bunch of algebra here. But I left like this because I think it's easier to digest. But this summation right here is this part, flow out, BT minus loss times flow in for B in batteries. And then we have our gen T, grid T, all added up, must be equal to double equal sign when it's as a constraint, total demand T. And then that's for each T in time period. So the next set of constraints I have here, I have the code, but I'll talk about it and then I'll give you another minute to see if you can think about what the formulation is. So sort of working backwards, given what we have, given the code that we have, can you come up with the formulation part, the algebra part? So the state of each battery is given at a time period, the state of each battery at a given time period affects the following state. So if I'm completely full of my battery is completely full, that's going to impact what the next state is. And if I'm completely empty and everything in between also. And what also is going to affect that is the decision to charge or discharge. So, and this is sort of why I had that question yesterday about like what happens with, the previous time period. So essentially we need to make sure we have a constraint that says at a given time, my state, which again, the decision variable is S. At a given state, I have what was there prior, plus whatever comes in, accounting for loss, minus whatever comes out. So here's the constraint written in Gurobi Pi. So this will give you like sort of like the form for it. But and notice that there's two sets of question marks, because what we have here is we have an initial condition, and then we have for everything past that. So let's take a minute to see if you can sort of at least partially work through what the constraints would look like in an algebraic form. I'm gonna add in the formulation part here. So I'll just go over this one because the initial condition is kind of the same. So the state of battery at time t is going to be equal to the previous state, whatever we have, plus the loss times what comes in, minus what comes out for each t greater than or equal to 1. So we're not having our initial state, which is taken care of here. And it's pretty much the same thing, but we're setting this, this value of what would be, -1 in a way, if this is 0. We're setting this at, we're fixing this as a particular number. So run that. Okay. So the available solar energy can be used in one of three places. It can be used, it can go directly to battery 0, it can go to battery 1, and it can also directly satisfy demand. So because we need to limit the amount the batteries can charge along with what's what is being used directly for demand. If we have in a certain period, like 30 kilowatts of energy that's going to be absorbed by that's going to be produced, sorry, not absorbed, that's going to be produced, then we can't use that 30 to satisfy demand while also charging our batteries. We have a limit for each period. So one more little, like, hey, let's think through it for a second. This time both things are missing. The constraint is missing algebraically, the formulation part, and then also the whole generator function for the constraint is also missing. So another minute to sort of think through that, and then we'll add that in and move on to the binary variables. So one more minute, or maybe one or two, since this is a double whammy. We'll give a couple minutes, and then we'll get back to filling this stuff in and moving along. So let's head back. So the formulation part is, we're saying that what the battery 0 charges, what battery 1 charges, and what is used to directly satisfy demand must be essentially bounded by the solar availability. So I'm just gonna paste this in. So essentially that works out to our flow in for battery 0 plus our flow in from battery 1 must be, and plus what we use must be less than or equal to our solar. And if you put the loss in here, that's the loss should come afterwards, but if you put it in there, that's, you're still quite close. And I'd still give you credit if I were actually grading this. But essentially, yeah, it's everything that we're using from the solar availability must be capped by that amount. So this is the solar forecast value, putting a bound on this sum. What does this look like in Gurobi pi? Well, it's flow, remember our flow in for BT. Oops. Since I wrote it out as battery 0, battery 1, I'll do the same thing here. You can use a quick sum over the batteries if you'd like. Since there's only 2, there's not much harm in typing it out. So flow in of battery 0 at time t plus flow in of battery 1 at time t plus gen t. So again, this is what we decide to use to meet demand must be less than or equal to solar values at time t. And I didn't include everything at this point. We need to add that part in there. So this is for t in time periods. and that should run. If not, I'll copy and paste and go. But all right, so far so good here. So now we're getting to like what I think is the little bit more interesting part, and why I like this example and examples like this. I like fun logic stuff. I think probably a lot of us do, and that's what modeling with binary variables really is. You need to take what someone says, or some condition, or some requirement, translate it into a logical statement, more or less. Take that logical statement and see how it works out from a logical way, how it translates to the inequalities, and making sure that what your logical statement says is directly represented by the numbers and inequality and inequality symbols and equations and all that sort of stuff, making sure that that's accurately represented. It's a little fun way to go about it. And there's often, people say that there's a little bit of an art to sort of machine learning in terms of, feature generation, coming up with new features, how you structure your data, how you do this, how you do that. You can also say a similar thing for optimization modeling, how you decide to translate the logic. There are ways that work and ways that don't work, but it's sort of up to you a little bit to how, and it is a little bit of a journey to sort of figure that out. So it's a fun part that I think about optimization modeling, and sort of why I find it so interesting. So I'm just gonna sort of describe the constraints and go through why they are the way that, why it works. And what you can draw, what conclusions you can draw from how this is formulated, because there are other ways that you can do it that may have some other advantages, may have some disadvantages. But again, as long as it works for what we want it to do and what we're going to claim it's going to do, that's the important part. So so let's sort of look at. So here's essentially the constraint is the flow in for each battery in each time. It's going to be less than or equal to 20 times our binary switch. Okay. And I'll explain where the 20 comes from at the end. And again, for each battery and time period, the flow out is going to be less than or equal to 20 times 1 minus our switch. So to sort of figure out how this works, let's just set the flow in for to sort of fix a battery in a particular time, doesn't matter which one, say battery 0 at time 20 or something like that, or battery 0 at time 1, anything. And sort of, let's just say that at that time we decide to charge our battery with 10 kilowatts, so F in is 10. For the first inequality to hold, if this is 10, then it necessarily pushes up the value of this, and we have 20 times either a value that's 0 or 1. So if this thing is 0, 10 can't be less than or equal to 0. 10 must be less than or equal to 20, making this making this value necessarily 1. So essentially, if our flow in is positive, then Z is necessarily 1. Let's think how that decision to charge at a particular time affects the flow out. So if this thing is 1, because it's necessary, this is 10, which then pushes up this, making this necessarily 1. 1 minus 1 is going to be 0. 0 times 20 is 0. So that necessarily pushes down the flow out to 0, because this is a non-negative value. It can't be anything negative. So 0 less than or equal to something that's non-negative must be 0. So by saying this value is positive, sort of see how, like, a little bit of the chain reaction here. This value is positive, makes Z 1. Z being 1 here makes this right-hand side 0, which then makes this left-hand side of the bottom inequality 0. And then the same thing applies for the other way around. If this is positive, then this is necessarily 0. because 1 minus 0 must be 1, and then this is 0, and then it requires this to be 0. So it's sort of like a cause and effect of if we decide to charge or discharge at a particular time, it makes it impossible to do the other option. Now, let's say that both of these things are 0. We do neither charge nor discharge. So if this is 0 and this is 0, it doesn't matter what values z takes. It could be whatever it wants to take, because 0 will be less than 0 or 20, and 0 will be less than 0 or 20 on this side. So in this case, z is sort of free to do whatever it wants. So that's an important thing to note about how we modeled this, because someone may come up to you and be like, hey, all right, I want to know the number of time periods that we charged or discharged each individual battery. And your first thought may be think, oh, well, I have a binary variable that should represent that. But given for what I just said, you can't just sum up your z's and say, oh, well, I'll add them all up and that'll be the number of times that I charged, because in cases where nothing happens, you don't know what z is doing. We're not making any requirements on it. So that's just something to keep in mind if you do model like this. You model these constraints like this. You can add a little bit more complexity to this to make that true, where that there's an equivalency here where Fn is positive if and only if zbt is positive is 1 as well. You can make that if and only if, you can make that equivalency, but that requires a little bit more logic in here, a little bit more stuff going on, and these sets of constraints work for what we want it to do. So and also, where did the 20 come from? That was the upper bound that I mentioned at the beginning. So essentially, this constraint takes care of two things. It takes care of the charge and discharge logic, and it also bounds our charging and discharging by the amount that we set at the beginning. So here are our constraints written out in Gurobi Pi. So it's just pretty straightforward. Flow in BT less than or equal to 20 times switch. And then again, this is for, I'm gonna sort of see if I can squeeze, yeah, there we go. This is for each battery and time period. So for each battery for each time period. And we can call this to charge, and then the other one to not charge. Although calling it that slightly off, but it makes things pretty clear. So I hope that made some sense. Understood the logic. Again, the whole point of this is to understand how, if a certain value is positive or a certain value happens, how it sort of pushes up and pushes down other things that are required by the constraints. So it's a lot of like sort of if then sort of thinking, conditional statements. So again, if this value is positive, then what must happen? By the way that we want this to happen. If this is positive, then this must be positive, and then all of the effects from there on out. So that was the part about using the binary decision variables. There is one thing that we haven't stated yet, and that is the capacity of the value, or excuse me, the capacity of the battery. So for each battery and state, we're going to do just a quick little for loop that sets the upper bound to it shows the upper bound that we're going to put on the state or on the battery. So how much that we can have in the battery at any given time, that upper bound is the capacity. And the reason I chose to do it like this, you could set these upper bounds, and we've done that before. We could set the upper bounds in the variable statement and add vars. But I decided to do it this way to show that you can do it a different way. And this is just, since this is all constant for B, it's just a little bit easier to do it with the for loop than if you did it in the add variable statement. You have to create like a whole list and stuff like that, and it gets it's a little bit more cumbersome to do it that way. So this is just as good. So I see a question, and this is a good question. If Z is a binary variable, how is it representing three things? Z itself is not representing the three different states. it needs to, the logic that is created represents 3 different outcomes. Z is only going to be 0 or 1. So Z being 1 does not necessarily mean that the battery is charging. And Z being 0 does not necessarily mean that it is discharging. It just means, again, so you got to think about it from a conditional statement point of view. We're not saying if Z is 1, then we're charging. We're saying if F is positive, or if we have flow in, then Z is 1. So those are 2 different conditional statements. So that's something to keep in mind of what we're saying. So it's important to understand the if then part of things, and then for an if then statement, the if part, if the hypothesis happens, then the consequence must happen. If A, then B. If A happens, then B must happen. If A doesn't happen, if this thing, if A doesn't happen, then we want to make sure that we don't impose any restrictions or anything like that, because we're not modeling for that part. So that was a good question. You just want to make sure that the logic is building in for what you want. But then again, we can definitely have more complexity here, and that could, you can have sort of sets of binary variables or something like that represent each of those states directly. That was a good question. Thank you. So back to our objective. What our objective is, we want to minimize the total amount of energy. Oops, and there's a little bit more here. That should be good. Pardon me. All right.
Jerry, just one quick note for everyone who has questions on the notebook that we are covering right now. If you could ask them in the Q&A function of Zoom, that's the place getting the quickest attention from the instructors and the Gurobi folks supporting.
Yes, definitely. And that's what I have the Q&A open, so I'm sort of, you see me glimpse up. I'm taking a quick look at that to see if there's anything that that would make sense for me to answer quickly. So yeah, definitely use the Q&A function. So back to the objective, we want to minimize the total amount of electricity that is purchased over all time periods. So quick sum over the grid for T and T in time periods, we want to minimize. So here is our objective. Make sure I didn't run all this stuff. I went past it and made sure I didn't run. Okay, we're good now. So I ran the upper bound, I ran all that. So let's optimize. We finally have everything. Yay. It took us a little while to get there, but here we are. So we can optimize, and we see that compared to last time, this was a very short log before. We have a little bit more happening. There's more, pre-solves doing some stuff, and there's a little bit more happening, but it still solves super fast. And I put down here to print out a statement of the total energy purchased from the grid is 1,281 kilowatt hours. So let's visualize what's happening here. So if you're running this on just the notebook itself, not in Colab, and you don't have matplotlib installed, it should have been, if you run stuff before, it should have given you a message there. But hopefully this should work out in a second. But what we're doing here is we're extracting the values of our variables. So this is the same as we've done before. We want to take our model, get the attribute for the particular variable that we want. This X represents the value of the decision variable. And then I'm printing out a few statements, just the number of periods in which the battery charges. So to answer that question, we're not looking at Z, we're looking at flow in and flow out, and when those are positive, because that's the actual indicator of what is charging. I probably could have made that distinction here. It could certainly be the case in which where it happens to work out nicely, but you don't want to make that assumption. So I'm extracting values. We see how often things are charging and discharging. Now let's do a plot of the battery states over time. And so you can sort of see I have a dashed line for the capacity of battery 1, a dashed line here for the capacity of battery 0. And you can sort of see how it's starting to charge, and then and then it discharges to meet demand, and it charges. This is at capacity, it comes down, so on and so forth. So it gives a nice little cool little just visual way of understanding how active our batteries are, and essentially how often are they at capacity. I printed out those values explicitly as well. So for 24 of the time periods, battery 0 is at capacity, and for only 10 time periods, battery 1 is. So let's also look at the amount that we buy from the grid. Let's plot that. So we want to sort of see, maybe it would be interesting to sort of see how these visuals sort of correlate a little bit. But so this is the amount of power purchased over the time period. So we could see that there are some spikes in which we really need to buy a decent amount. And then there are a decent amount of periods where we have nothing. And what I counted here is the proportion of periods in which electricity was purchased. So the number of times in which that grid variable is positive, and it's about half the time. So we have about 9 minutes left. So let's dive into changing the objective, because that'll take going through this maybe a little bit faster than I had thought. But that's good. I think, and if any things are unclear, we should have a couple minutes at the end. I can sort of go through some of that as well. So let's change the objective to do something that may be a little bit more realistic. Our initial objective was, let's just minimize the total electricity bought from the grid. So we want to be as sort of as independent as possible, energy independent as possible. That may not be the most cost-effective measure, though, because as I'm sure we all are very well aware, that the cost of electricity, the cost of energy, fluctuates somewhat drastically during a day, and it's and distilling this to 30-minute time periods does not do it justice to how often the costs change. So and that's data that is freely available to, I believe, by local, by areas and stuff like that. So it's a cool data set to dive into if you're interested in energy and also interested in sort of time series stuff. It's a nice little way to get exposure to that. So if we want to change our objective to minimizing the overall cost of purchasing electricity from the grid, that's a little bit of a different objective, but we need prices. So we'll read that in from our data set. And again, this is another way that you can sort of see how a very complex sort of machine learning model or models can be used to estimate a lot of this stuff. We sort of just did we just used time series forecasting to build a forecast for the solar availability. And then we just sort of said everything else we know, or we're going to assume, or something like that, including the price. But you would definitely want to build some models or do at least some sort of analytic process to understand what the price is going to be as well. To create this, I think I just averaged over a bunch of days to come up with, hey, this is what we think that the price would be. But again, you can get more sophisticated there and dive into doing this on your own to build something that will give a little bit more of a realistic price, possibly. But this is what the price looks like over each time period. So you can see some decent jumps quickly, and then some periods in which it's fairly constant. But here's our nice visual of what the price is going to be. So to set the objective again, all we need to do is just use set objective yet again, and it will just overwrite right there. So essentially what we want to do is we want to sum the price times the grid value, and then sum that all for each time period, for each time in time periods. And notice one thing that I mentioned this before, that throughout all of these notebooks, we always use the same index that we would iterate over for all of these 4 statements and things like that. You don't need to do all that. We don't always need to use T. In this period, I just wrote time instead, because my iterator for this is time here. If I put just T at this point, then I'm in some trouble. But as long as this matches what's in here and in here, we're good. And as long as the set that I want here is the right set that I'm looking for, then we're good. So we don't have to worry about what these individual values are, as long as it all matches up. And then we can optimize that. It solves quite quickly. And then we can extract the solutions again. And then we can sort of compare the visual here from what we had before. So what we notice comparing this visual to the other, let's look at these numbers real fast. I'll scroll back up. We have 27 time periods in which battery 0 is full, and 15 for battery 1. Scroll back up, maybe a little bit too far. We have 24 and 10. So we could see that each battery has increased the number of periods in which it's at full capacity. But then also looking at sort of where that happens and how it's happening. We have some flatness here and here when we're at capacity, but there's little dips, and just some short peaks in which we hit the capacity again. Scrolling back down, we can see the effect of changing the objective to including price. We have a lot more flat plateaus. We get to capacity and we stay there. And we stay there until it's much more beneficial to use the free energy that has been stored rather than buying it. So you can sort of see how the 2 different objectives impact what our batteries are going to be doing. So we're pretty much running at almost the exact amount of time. So a couple more bonus questions to look at. Some follow-on questions is, how much electricity was purchased from the grid after changing the objective? How much did that, are we buying less, are we buying more? Because again, those are 2 different things, we're not going to end up with the same amount of electricity necessarily, because one is just, hey, I want to minimize the total amount of electricity, and then the other is I want to minimize the cost that's associated. So calculate that out and see how that changes. Given the prices used for the second objective, so what we just did, what would the cost have been? So if we, in our decision problem, if we had our objective wrong, in terms of what we really wanted to do in our business problem or decision problem, what would the cost have been? And then how do you think increasing the capacity of battery 0, which is the one that's been hitting its capacity a little bit more, how would that change the both objectives, but essentially the second? So maybe just play around with that as well. We have a bunch of, if energy modeling is something that's interesting to you, immediately before I came to Gurobi, I did work at a cool energy consulting company named On Location in Northern Virginia. Great folks there, and some really interesting problems that they would tackle. So we have a bunch of examples that relate to energy in our set of notebook examples. So check those out as well. I don't see any particular questions at the moment. We are 1 minute away from the next session. So for that session, we're going to be looking at exercise set 2, which you can find in the GitHub repo, and also in the Whova app. In the event for this, there should be a link to that for Google Colab. So we are staying in this Zoom link. So what I'll do is probably give just like a quick minute or two, however can catch their breath, particularly me, and then we'll come back and dive into the second exercise set.